This is an example problem in which we have an insulating sphere. I should put that on here, insulating. We've got an insulating sphere on which we've placed a charge distribution which is not uniform, right? We've seen several examples where the charge distribution of insulating spheres is uniform, or usually that said a sphere of radius r charged uniformly to some charge q, and then you can form your charge density as just q over the volume. But in this case, the charge density is actually a function. I've got some alpha r here, where alpha is some constant with appropriate units. We don't need to know what it is, but it's some constant. So this is what my charge distribution looks like. I'm probably going to be finding the electric field somewhere inside, and so let me give you my Gaussian surface inside. This has some radius r. We'll let my sphere have some radius a, where a is a constant, but r is going to be my variable. I need my Gaussian sphere to have a variable radius because I need to determine the electric field everywhere. So inside, if I'm going to find the electric field inside this, my Gaussian sphere is going to be placed inside, concentric with the actual sphere, and I'm going to form Gauss's law like this. Electric flux is equal to integral over the surface area. Sorry, this is the not Gauss's law. This is the definition of electric flux of E dot dA. And then by Gauss's law, that is equal to Q enclosed over epsilon naught. Okay, so on the left-hand side, we've seen this a few times. I think we're going to be able to figure out easily that E and dA are everywhere collinear. So E dot dA vector just becomes E dA integral E dA. But as long as I've at the same radius, E is constant, comes out of the integral, I'm left with just EA, and then I know the area of a sphere. It's 4 pi r r squared, where this is the radius of my Gaussian sphere. So that was a lot of talking and some sort of hand-waving sorcery. If that was Greek to you, I think you might need to go back and watch some previous videos where we talk about that a little bit more. I'm assuming that we know how to do the left-hand side. The right-hand side is what I'm going to look at for this video. So you should have already watched the video about differential volume elements in spherical symmetry. If you haven't, go back and watch that one. The challenge here is determining how much charge we have enclosed in my Gaussian sphere here, because I've got this charge density, which is a function. But I still remember that anytime I need to undo a density, I just multiply by what the density is formed with. In this case, this is a volumetric density. And so if I multiply this density by a volume, if this is a charge density times a volume gets me back the charge. And so I can write Q enclosed as my rho dV, where that's my differential volume element. I'm assuming, of course, that I'm going to have to integrate this. So this is my charge density times volume. Of course, this is dV because this is a volumetric charge density. If this had been an area charge density or a linear charge density, I would multiply by the appropriate element. But in this case, this is a volumetric charge density. I know because it says rho and not sigma or lambda, right? That's the standard, or this is the convention for volumetric densities. So rho dV, and then I'm going to have to integrate my dV. I've got to do this because this is a function, and I can't just say, well, whatever it is times the volume. No, I actually have to do the integration because this is not a constant density. All right, so let's pull out what we can here and rewrite what we can. So I'm just gonna move over here. On the left-hand side, I still have E times 4 pi r squared. We're working with the right-hand side. Rho is not a constant. I cannot pull it out, but I can pull out 1 over epsilon naught. And then on the integral of alpha r, that's rho times dV. Now, again, we're going to unpack what dV is in a second, but notice, even though my charge density is not constant, it involves a constant alpha, so I can pull alpha out. So I'm going to get alpha over epsilon naught. Now, let's actually pull out what my dV is. Remember, there are three distinct differential elements in here. There's a dr, there's a d theta, there's a d phi. This is going to be a triple integral. Why don't I just go ahead and write it as a triple integral. Not triple, that's not a word. And what do I have here? Alpha, oh, I've already pulled out alpha. I've got r from here. This is part of my density, but my volume element is now r squared sine theta dr d theta d phi. Again, if that's Greek to you, well, it is Greek because you got theta and phi, but if you don't know where this comes from, go watch the previous video on differential volume elements. Let me clean this up and separate out my integrals. You don't have to take this step, but I always like to. And put in my limits. I'm going to have r cubed. Notice I've got an r here from the actual density and an r squared from my volume element. So that becomes an r cubed dr. The limits of that are going to be from 0 to a, because that's the limit of my sphere. And then I've got a sine theta. Sorry, I should put an integral there. Sine theta d theta. We saw the limits in the other video from 0 to pi. Then I've got integral d phi from 0 to 2 pi. Again, if you have not watched the other video, go watch it, because I'm about to do a little bit more sorcery. In the other video, we saw that there, as long as I don't have anything in these angular integrals besides this sine theta, and these are the right limits, every time I evaluate the angular integrals, I get 4 pi. Now, again, if there is an angular dependence of your charge distribution, in other words, if this is not alpha r, if it's alpha theta or alpha phi, you cannot make this assumption. But in this class, which is Physics 2, University Physics 2, we are not going to give you any angular dependence of your charge distribution. If you do, you have to go to other systems. Here, we're going to evaluate the angular integrals as 4 pi. Do the evaluation if you need to, or you can just memorize that it's 4 pi. If you're in my class, I'm okay with that, as long as you can show me where that comes from. Yeah, you have to understand it. But as long as I can do that, I can now evaluate the dr integral simply as r to the 4th over 4. This is an epsilon naught. And then I get a 4 pi here. So let's write out what we have. I've got an alpha over epsilon naught from the constants. This gives me a 4 pi from the angular integrals. Those are constants. Angular integrals. And then my radial integral gives me r to the 4th over 4 evaluated from 0 to a radial integral. That's just going to come out as a to the 4th over 4, but I'm going to lose one of the 4's, notice. And what this ultimately gives me is alpha over epsilon naught pi a to the 4th. Now, remember, this is equal to, I still have stuff on the left-hand side, e times 4 pi r squared. I'm going to lose the pi. I'm going to pick back up the 4th. And then if I evaluate the electric field here, I'm going to get alpha over 4 epsilon naught r squared a to the 4th. And that's the magnitude of my electric field inside the sphere. Now, if you remember, when I did the problem with a constant charge density, I did not get a 1 over r squared dependence here. So having having a linear r dependence in the charge density ends up giving me this r squared dependence here, 1 over r squared dependence, which is interesting. But at any rate, this is the electric field inside the sphere as a function of r and as a function of this constant, which is a characteristic of the charge density. If you go outside the sphere, of course, it functions as a point charge. You can then just use the same technique to determine the entire charge of the sphere if you don't already know it. Sometimes you do, it's given to you in the problem, and it functions as a point charge. It goes 1 over k times, or kq over r squared, basically outside the sphere. But the purpose of this example is to show you how to handle inside the insulator when there is a non-uniform charge distribution.